So, Osmocom-GMR, it's one of the latest member in the Osmocom family. I'll start with a quick introduction on GMR generally, then a technical introduction on GMR1, and finally the software itself that we wrote and how to use it. Okay, so what is GMR? GMR stands for Geosynchronous Geostationary Earth Orbit Radio Interface, and it's an ETSI standard for satellite phones, so essentially these phones. ETSI is the same body that standardized GSM, and they reused a lot of their specification for GMR. And if you read the GMR specification, you will find lots and lots of reference to the GSM specification, sometimes referencing entire chapters. GMR is two distinct standards called GMR1 and GMR2. They are not evolution one of the other. So GMR2 is not a replacement for GMR1. They exist in parallel, and they've been developed by different vendor groups. In this particular talk, we'll talk only about GMR1, and more specifically, the first of the 3 revisions. So the first revision, just called GMR1, is the equivalent of standard GSM to 2G circuit switched, so essentially voice and SMS and nothing else. A later revision came, and it's called GMPRS, and it's obviously the equivalent of GPRS, basically adding packet data over GMR. And finally, the latest revision is GMR1 3G, which essentially adds more channel types for higher bandwidth and also interoperability with the UMTS core network. So where is it used? One of the most important deployment of GMR1 is the Thuraya satellite network, and it's the one we studied because it's the only one visible from Europe, and since most of the, actually all the developers are in Europe, that's the only one we can receive. More specifically, the Thuraya 3 satellite, which is at orbital position 44 east, is the only one we can see exactly from here. There are other deployments, for example, SkyTerra and TerraStar are in the US. The other ICO I don't really know well, and Inmarsat was actually at some point just renting capacity on the Thuraya satellite and didn't have its own satellite. GMR2 is used in the Inmarsat iSat phone, which is a quite well-known network as well, but we won't go into further details. So this is the coverage map for the Thuraya network, and as you can see, it pretty much covers everywhere except the Americas. But here in Europe, we are well within the optimal coverage zone, and so receiving it is not a problem. So it's heavily based on GSM, so it makes sense to compare it a little bit. So the first thing they did is they renamed everything. They changed basically the B into the G for, of course, gateway or geostationary, depending on the type, and the MS, which used to be the mobile station. So your phone is now called MES, which is Mobile Earth Station. They introduced some useful stuff, so specialized features. One of them is the terminal-to-terminal calls. So if from a Thuraya phone you call another Thuraya phone, to avoid to go through all the way from the phone to the satellite, to the core network, back to the satellite, back to the other phone, they introduced a shortcut where a phone can talk to the satellite and directly be bounced onto another phone without ever going through the core network. And another feature, it's called high penetration alerting. And this is because satellite phones don't, at least these models, don't work at all inside. You need almost direct line of sight to the satellite, so to the sky. But you still want to be able to receive calls when you are inside, and so they have some very specific channel types that have much higher coding gain, so that when you're inside, you cannot place calls, you cannot receive SMS or anything, but you can at least have a notification that, okay, someone is trying to call you, you have about 20 seconds to go outside and get the call. So that can be useful. It has very tight link to GPS from the start. For example, all the almanac and ephemeris data from GPS are sent from the Thuraya satellite to help the phone get a GPS lock much faster. And the phone will actually report its position each time it opens the channel to the satellite, so that the satellite knows exactly where you are. They introduced a new codec because of bandwidth limitation, and they invented a new Cypher, but we'll talk about that later. From a protocol stack point of view, the radio frequency layer and channel coding layer, so the lowest layer of the stack, are completely different. You find the same concept, but all the details are really different, so different bursts, different modulation, a lot more channel types to handle special cases. Above that, you have the data link layer, which is called here LAP-SAT instead of LAPDM. Both are based off the LAPD in the ESDN world, but they've been adapted for the peculiarities of satellite, that is very, very long delay, because the satellite is like 36,000 kilometers in the sky, so for each round trip time it's like 240 milliseconds, which is quite high. On the layer 3 level, I will detail all the layer afterwards, but quickly on the layer 3 level, the RR, which is radio resource, is again completely different, and we'll see how it is different. Everything above that is exactly the same as GSM, so no difference whatsoever. Small peek into packet data, the situation is similar. That is, the lower level, which are RLC and MAC, are different, but LLC and above are completely common. So this is an overview of a GMR network. And you can see the protocol stack on the bottom. Everything that is in color is specific to GMR. Everything that is in white is common with GSM with no modification whatsoever. So as you can see, everything that is in the core network is shared with GSM, exactly the same. So in detail, you have the satellite, which communicates with the phones on Earth, obviously, using what's called spot beam. So they are the equivalent of cell in the GSM world. Spot beams are artificial small zone of coverage that are generated by the satellite using beamforming algorithms. Of course, when I say small, it's small at the planetary level, so it's like 100 kilometers wide. It's not that small, but something like that. The signal is bounced back to what's called the GTS, a combination of the GTS, the GSC, which is a gateway transceiver station, and gateway. It's GCS actually, if there is a typo. It's a gateway controller station. And from there, it goes through the GSM core network, so MSC, HLR, typical GSM stuff. Something that's interesting to note is that the satellite only plays a role at the physical layer. So data link layer is entirely handled from the phone to the gateway station, and it's not touched at all by the satellite. The satellite doesn't have much logic. It just bounces back the signal into an aggregate feeder link. So as I said, the physical layer, using for the communication between satellite and phone using spot beam. It is a frequency duplex like in GSM, so you have a part of the band that's reserved for communication from the phone to the satellite and another part of the band that's reserved for the inverse direction. It's divided into RFkin, 1087 of them, which are not actually very wide. They're only 31 kilohertz compared to GSM, which is something like 280 kilohertz. So they are very small channels. The feeder link, so that's the link between the satellite and the main gateway station on Earth, can happen either in C-band or in K-band, but that's about all that's said in the specification. There is no other technical detail available, at least publicly. to what exactly happened on that feeder link. So let's take a look at the physical layer in a little more detail. As in GSM, it's entirely synchronous, a complex TDMA scheme. In some aspect, it's simpler than GSM. In some aspect, it's more complex than GSM. It really depends on where to look, but basically, they have to take into account power consumption, because something very important on the satellite is that there are some broadcast information that is sent permanently, all the time, periodically, I would say. And they have to make sure that they don't transmit that information at the same time in all the spot beam, because this would create very high peak in power consumption on the satellite. And so this is reflected somewhat in the TDMA alignment, and you have to take care of that. Major difference compared to GSM is that so you can see one of the TDMA frame here is composed of 24 time slots, and the burst, that is the packet of information exchanged on the network, can occupy several consecutive time slots, which was not the case in GSM 2G at least. One of the main problems in the physical layer is the synchronization. That is, when a phone is powered on, it needs to find the carrier, essentially. So it needs to detect, is there a carrier on that particular frequency? How is it aligned in time? And what is the frequency error? Because demodulation requires a very precise synchronization between the clock of the cell phone and the clock of the satellite. And the crystals and oscillators used in the phones are not that good, and so the error must be detected and compensated. And I think they found a very elegant solution in this particular waveform, which is called the dual chirp. So a chirp is single tone that is varying in frequency over time. The graph, the picture represents frequency vertically and time horizontally. And so you can see that you have two spikes in frequency that crosses each other over time, drawing kind of a X in the waterfall display. And I won't go into all the mathematical detail, but this waveform has very interesting property. Most notably is that if you capture roughly where this waveform is using you do a rough acquisition by a simple correlation, it won't be very precise, but it will be good enough to know more or less where it is, like in this window. And then you multiply that by a reference upchirp, so only the ascending part. You do the FFT, and you take the peak frequency of the FFT, you call that F1. You do the same time for the downchirp. And kind of magically, the time alignment error will be proportional to F1 minus F2, and the frequency error will be proportional to F1 plus F2. If you're interested into why exactly that is, you can follow the link. There's a very interesting paper about it. Packets of information are exchanged in bursts on the physical layer, and they are modulated using what's called a Pi4 QPSK, which is a modulation which is completely different from GSM again. There are two slight different variations. One uses a quad-phase shift keying, the other only has two-phase shift keying. But these are the two modulations that are the most used onto the physical layer. They are relatively easy to demodulate, and we'll see that later on. There's a lot of different burst types. Too much to list here, but it's the modulation doesn't change between them. There are other types of channels that have very specific purpose, like for example the high penetration alerting has a very specific type of burst, and there are some keep alive bursts that are used in very specific cases that uses different modulation represented on the bottom. And also for GMPRS and 3G, you have more modulation types that can be very, very complex. You can see the constellation pattern of 32 APSK is much harder to demodulate and to increase the bandwidth even more for packet data. Instead of using the base symbol rate of 23,000 kilosymbol per second, they can actually use either twice that symbol rate, 4 times that symbol rate, or 5 times that symbol rate to just put even more data on the same channel. Okay, so this was the RF layers. The channel coding layer is what will take care of taking the layer 2 frames, breaking them into bursts, and ensure that they're transmitted correctly by applying error correction and error checking. Every channel type in GMR uses, of course, a different method for it, but hopefully they all use the same basic primitives, so that's kind of good news. And we have implemented all of these. So essentially, it's the same primitives that are used in GSM and a lot of other protocols. That is convolutional code, CRC checking, scrambling to avoid runs of 0 of 1 that would pose problem in the modulation stage. And something interesting is you can see here is the encryption is applied in layer 1, like in GSM. Okay. LAPSAT is the data link layer. Honestly, I think it's a bit, it's not a very interesting layer, but its role is mostly to take the variable size L3 messages and split them up into chunks that fit into bursts and ensure things like retransmission in case packets are lost, things like that. So layer 3 is kind of the, let's say, the application layer or something. Its lowest sublevel is called radio resources, and it oversees the establishment of dedicated link between the phone and the satellite. This layer is completely different from GSM, which is kind of logic because the kind of radio resources that are managed are different. You will find the same concept. So, for example, you will find immediate assignment message. You will find paging messages. Actually, you will find exactly the same types of messages, but the detail of how they are encoded and the information contained in them is different because of course, the detail of the physical layer are different. The upper layer, mobility management, which provides user location tracking and authentication and confidentiality, so exchanging the IMSI for the TIMSI, things like that. And the connection management layer are all common with GSM, and so we can reuse all the code that we already wrote for those. Okay, the speech codec was, as I said, they used a new codec called AMBE, or at least the codec family is called AMBE, standing for Advanced Multiband Excitation. It's low bit rate to feed the need of a satellite channel. Unfortunately, it's proprietary by a company called Digital Voice System Incorporated. There is no public specification whatsoever, and there is no reference implementation provided, which is kind of a problem for us, because that means that we can't neither decode nor encode speech data. Hopefully there is kind of two ways we can get around that. The first one is called MBE-lib. So the same family of codec is used in APCO 25 and DMR, if I remember correctly. And someone implemented those particular variants. They are different from the variant used in GMR, but at least some of the concepts are similar. Unfortunately, the author is anonymous, and we have no way to contact him to ask him to see if he has some clue about how to decode GMR frames. So if by any chance you know him, you know. The other lead we have is that, well, the phone codec is obviously implemented in the phone. Most likely in the phone DSP, because the phone DSP is a TI DSP, and what a coincidence, DVSI provide TI DSP code source for their codec. So we could most likely try to find it in there, but this is going to be a lot of work. And so if there is a way to bypass that'd be nice. From a security standpoint, a few words. There is some good and there is some bad. I'm not sure if the good was intentional or just a byproduct of other decision, but it's there. The first good news from a security standpoint is that the contention resolution does not echo the first message. So let me explain that a bit. In GSM, something for an attacker, something that's very useful is that the first message sent by the phone to the network has two interesting properties. The first one is that it will always contain some form of unique identifier for the subscriber. Either it's IMSI or it's TIMSI. So that allows you to identify the channel. The other nice property of this burst is that the BTS will actually echo the content of this burst during the contention resolution procedure. That means that even if you can only listen on the downlink, which is very common, you still can attribute a given dedicated channel to a given user. And this is something that has been used to do targeted sniffing on GSM and things like that. In GMR, this is not the case. Technically, it could be echoed, but there is another option, and that other option is what is always chosen as far as we can tell, is that it will transmit like a CSC or a hash of the original message. So the phone can still know if it was its message or not without actually revealing the message to the entire world. Another feature is that DTX, so this is discontinuous transmission, is heavily used in GMR. As I previously said, power consumption of the satellite is pretty important, and so when the satellite has nothing to say, it does not say anything. Contrary to GSM, where on control channel, if the base station didn't have anything to say, it would just send an empty frame that is completely known and would provide lots and lots of known plain text for an attacker. In GMR, this is not the case. If the satellite has nothing to say, it would just say nothing. And so you don't have as many plain text as you would have in GSM. Of course, it's not all good because it's heavily based on GSM, and so some of the things are inherited. The security is entirely optional. Hopefully on Thuraya, they actually use it. Some of the GSM attacks should be applicable as is. Most notably the FCCH denial of service and the IMSI detached denial of service. I say should because we haven't tested them. For GSM, it was easy for us to set up a test network where we can test that in a controlled environment without impacting commercial network. Here we can't really start a denial of service attack on a satellite. I think they wouldn't like that. Something else that's pretty bad is that the phone transmits lots of private information in the FCCH. So when you take your phone and try to place a call or power it on or do any kind of transaction, the first thing it will need to do is establish a dedicated channel between the phone and the satellite. To do that, it transmits what's called a request access burst in the FCCH. And here, this burst actually contains lots of information in clear text because there's no way to cipher it yet. Like the position of your phone, so each time you establish a channel, you essentially broadcast to the entire world where you are. And also why you want a channel. And in the why part, if you're actually placing an outgoing call, this will include the number that you are dialing. So it's bad, obviously. And finally, the Cypher is still applied at layer 1. About the Cypher itself, it's currently unknown. It's supposedly derived from A52. The spec kind of strongly hints at that, and some other people have told us that, but that's about all we know. We actually tried A51 and A52 just in case it was that, and we tried some minor modification on them, but it didn't work. So yeah, we're looking into it. However, we can still look into what could we do once we get the Cypher. As I said, the availability of plain text is going to be more limited than in GSM, mostly because of the discontinuous transmission, so there is no idle frames that we can use. Another source of known plain text in GSM was the SACCH, so a slow associated control channel. That was basically a channel that kept repeating the same thing over and over again. That channel doesn't exist here, so no way to use that. And finally, the actual channel burst have a lot less bits per burst, meaning you have, even if you have known plain text, you have less of it by burst that you can exploit. Although we don't know the Cypher, we know that, well, past experience has shown that the kind of protocol they standardized, like A51, A52, GA1, GA2, were not especially strong. So, especially if you just Google for like a Thuraya intercept, you will find commercial crackers that claim that they can intercept the channel in a few seconds. So you can kind of imagine that the Cypher must not be that strong if it can be broken in a few seconds. Okay, so we'll now look at the actual software stack we wrote. But first, a bit of history about this project. So, as I said, it's relatively new. It was started around mid-July when Harald sent a mail saying, yeah, I've been looking into GMR with Dieter, and he started a wiki where information started collecting. A few weeks after that, Dimitri actually managed to receive the first signal from the satellite and seen them on the FFT. And if you remember the slide with the FCCH, you could see the cross pattern on the FFT is very clear. You just can't miss it. The signal reception work was continued at CCC camp. If you went by the radio tent, you should have seen the satellite dish outside. And finally, in September, around mid-September, we had the first packet being demodulated, and we started analyzing them. It took some time to clean the code and make something that we could release and that other people could use. That happened somewhere in October. And more recently, we added support for TCH3 channel types. So Osmo-GMR is more than just the Osmo-GMR Git. It's composed of several parts that work together to create a reception chain. It all starts with the capture utility that essentially captures the radio signal and saves it to a C file, so complex samples are very common in software-defined radio. Those are processed by the GMR1 RX, which is our main test software application, and they're forwarded or to an extended version of GSM Tap to Wireshark, where we can see the packet content and start looking into the data that are exchanged. So let's start with capturing. First step is the antenna. Essentially, anything that can receive the correct band of frequency with left-hand circular polarization is going to work. Omnidirectional are not especially good, so you really need something kind of directional. But it can be quickly hacked together. The first version was a satellite dish, which had very good gain and very good directivity, but unfortunately is not very practical. The second antenna that was built was a helical antenna, and it's a fairly good trade-off between performance and convenience. And it's relatively easy to build. You can build one in a few hours. And Steve actually tried a B-quad that seems to work very well, and is also very easy to construct from PCB etching. So the details for this one are not on the wiki yet, but hopefully they will soon be. Once you have captured the signal through an antenna, you can go through the optional step of amplifying it and filtering it. Both the steps are optional because since we are in the optimal coverage zone, the signal is quite strong enough that if you have a fairly good antenna, it's going to work just fine. However, maybe you want to receive more than just the primary spot beam. Maybe you want to receive spot beams that are not standard to your particular location, and you want to look at the neighbor spot beam, and those will be weaker. So you need to amplify the signal to get it out of the noise. If you are near a strong transmitter, you also may need to filter the signal, because 1.6 gigahertz is kind of near some strong carrier, and if you have too much gain without filtering, you might end up saturating the input stage of your software-defined radio. There are various options available. One of the cheapest way to get a working amplifier only is actually to use a modified GPS LNA. So if you know those GPS antenna that you can buy for very cheap, they have like a ceramic antenna on top, and you can just remove the ceramic antenna, remove the GPS filter on the PCB, and just use the LNA on the antenna. And since the GPS frequency is actually pretty close from the GMR frequency, they will work just fine. So capture hardware. You can use any software-defined radio you like as long as it can save C files. But our capture utility has a specific support for UHD. So basically, any Etus hardware there is, you should be able to use, as long as you have a matching daughter board for the correct frequency, of course. One interesting particularity of the USP1 is that since you can put two daughter boards, you should be able to listen to both uplink and downlink simultaneously. It should be possible with the other Etus products, but you will need a GPS 1 PPS pulse to synchronize the various USP between them. So it's a little bit more complicated product setup. Sorry. The cheapest option you can have is the FunCube Dongle Pro, which is this little USB stick that has been released some time ago, which actually works very well for GMR. It has a small bandwidth, so you can't capture a lot of RF simultaneously, maybe 3 adjacent channels at a time, but it works very well, and it has actually pretty good sensitivity, and it's been used successfully. And soon, obviously, there will be the Osmo-SDR, which is a new project Harald announced not so long ago on his blog. The software used for capture is called GMR Multi-RX. It's based on GNU Radio and will handle all the nasty details for you. It will choose the optimal frequency to tune to avoid the DC peak, so that you don't have the DC peak in the middle of your signal. It will automatically channelize and resample so that the demodulation part has a nice 4 samples per second or something. And all you have to do is really, you just compile it for the hardware you want, and then just give him the frequency you want to listen to, and it will just figure out everything else itself, and you will end up with 2.c file that you can feed to the next step of the process. So when we started writing the actual software-defined radio part for Osmo-SDR, we realized that we didn't have a lot of the mathematics helpers that were required. And so we created a very simple library that has just what we need, and that fits very well with the other Osmocom library. This one is called the Osmo-SDR, and essentially what it is support for complex vectors, so IQ data, and a very common operation on them, like removing the DC offset, convolution, correlation, basically all the small primitives you will need when you implement software-defined radio. The actual software-defined radio part of Osmo-GMR is located under SRC SDR, and it has several jobs. The first of which is FCCH Acquisition. So this very specific waveform, the process I explained with the correlation and the FFT, it's implemented in there so that given a random capture, we will need to find first, is there a carrier at all there? And if there is, what is the proper alignment and the frequency offset to compensate for it? The process we have works very well, and it can actually find multiple overlapping carrier. Because of frequency reuse, you can sometimes have channels where you have two carriers at once that are shifted in time, and the implementation we have can manage to lock to both synchronization and extract data from both overlapping channel. So obviously we need a demodulator to get the data out of the burst. So we just wrote a generic QPSK demodulator and the CBPSK, so it's handled as a special case. And this layer also contains the description of the various burst types. So you have SDCCH, TCH, the various training sequences that are used and everything. And it's all in library form, so this layer is essentially a set of primitives to be used by some application to perform the functions. It's currently reception only, so only the demodulation part, but writing the modulation part should actually be easier because modulation is just generating the proper signal envelope and mix it with the transmission window. But it's something that we haven't done yet. So layer 1, that's the channel coding layer. We have implementation for some of the primitives, so essentially scrambling the various convolutional codes that are used in GMR, puncturing all the CRC schemes that are used and the interleaving schemes that are used. And we also have stateless coders and decoders for some of the channel types. The most important one being the BCCH, which is the broadcast channel. So that's essentially the system information messages that describe the network and tell the phone what network he's on, what are the neighbor cell and things like that. CCCH for paging and immediate assignments. And FACCH3 and TCH3 are the actual traffic channel where user data is exchanged. So these are dedicated channel. This entire layer supports encoding and decoding completely. So obviously, since both previous layers are just primitives and the helper function, we need something that actually uses them. Usually it would be the higher layer, like layer 2, layer 3, and stuff like that, but we haven't actually coded that yet. So instead, we have a test application whose main job is just do the equivalent that AirProbe does for GSM. That is, you give him a C file where you think there is a carrier. It will try to acquire synchronization, extract all the broadcast channel types like BCCH and CCCH, and if by any chance on the CCCH it sees an immediate assignment to supported channel types like TCH3, it will follow it, decode the TCH3 data, and forward all of that to GSM tab for further analysis on Wireshark. So Wireshark. This was actually a lot of work because you don't realize it when you use Wireshark, but writing the dissector that displays all the data nicely is kind of a painful process. And now I am very grateful for all the developers who actually implemented all the protocol that I analyze. So what has been implemented is the data link layer, LAPSAT, is completely implemented. The BCCH is partial. You will see in the capture that I will show that we only decode some of the system information messages because they are coded in a very annoying way. That is, they are unaligned bit fields described in a CSN1 concrete. If you saw the talk by Harald, it's the same CSN1. CCCH, the dissection is incomplete, but we have support for all the message types that we have seen so far on Thuraya. So even though we don't support like the dozens of types of message that are described in the specification, every message you see should be dissected and displayed properly. If you find one that isn't, keep the capture, post it to the mailing list, and we will add support for it. Same thing for the RR layer, radio resources. That is all the message we've seen so far dissected. The upper layer, since they're completely common with GSM, we obviously didn't rewrite the code, and we just forward those data to the pre-existing GSM dissector from Wireshark. So we can take a look at what a GMR signal looks like. So this is a representation of a GMR signal. So on this axis you have the frequency, and this is time. And so you can clearly see here the synchronization pattern, and then all of this is there is just no transmission. It's slightly lighter blue than this because this is actually filtered out by FIF filters to channelize the thing, but this is just noise. And here you have the burst of data. Those small bursts are actually the GPS ephemeris data that are transmitted periodically so that the phone can lock on, at least is supposed to lock on faster. Not sure it actually works, but this is BCCH and these are CCCH. But as you can see, once you see that if you're trying to receive GMR, you just display it in a waterfall display. And if you can see this kind of pattern, you know you found a GMR carrier. There's just no doubt about it. It's very distinctive. So, well, obviously I can't really capture a signal live because, well, we're inside. But I have some pre-recorded signal that I can process. Yeah, unfortunately, it's not really readable on the screen, but Wireshark should be readable. Let me launch Wireshark. So here I'm just calling the main application. So yeah, you can't read it, but it says GMR1 RX. The first argument is 4. It's just the number of sample per symbol. 4 is the optimal value, so just use 4. Then I can give him 2 C files. The first one is the BCCH, and the second one is where the TCH is going to be assigned. Because we can't currently follow live, you have to kind of know where the TCH are going to be assigned. Hopefully in Thuraya, you just take the BCCH number, you add 1, and the channel are going to be assigned there. So that's pretty easy. And when you launch it, it will just decode everything pretty quickly and forward everything to Wireshark. So what can we see? The first thing you can see here is the BCCH, so they're the broadcast information, and as you can see, the dissection is somewhat complete until you actually reach here. The actual message content is not decoded. We only have support for a few segments. Segment 2A, which contains all the synchronization information, like the current frame number, and some offsets. And another type we support is segment 3A. And this one contains very interesting information because it broadcasts the name of the network. I mean, the name is the MNC MCC. So you can see 901.5 is the code for Thuraya. You can find the location area code, which in GMR is split between the MSC ID and what's called the spot beam ID, so just the number of the spot beam you are on. And more interestingly, you can find the beam center position. So you can know that this beam is actually centered on those GPS coordinates. And one of the first things we did is just try to map all the beam that we managed to receive. And these are the beam center position of all the beams we've been able to receive so far. The reception was some from Belgium and some from Germany. So you can see that you can capture data from beams that are pretty far away. Our current assumption is that the beam forming algorithm has some side lobes, and we are seeing those side lobes mostly here. So all these are broadcast information, but of course, at some point there will be. Let me find it. Okay, so here you can see an immediate assignment. There's a channel is being assigned, and this was actually me making a call, and you will find the channel description that says, okay, go to ARFKIN 268 on the time slot 13. And if we filter by channel type and only display the dedicated channel, you can see here all the communication that has happened between my phone and the network. So first, Ampliframe with nothing, and then you can see the authentication request exactly the same as in GSM. So because since this is done by the mobility management layer, it's common with GSM. And then you can see the ciphering mode command that activates ciphering. And you can see it requests A51, which is not actually the same A51 as in GSM. And it also, for some reason, transmits a string that tells the phone to display Belgium on the display. I have no idea why they put that in the ciphering mode command, but they did. And of course, after that, you can't see anything because it's ciphered. And although it's my phone, I have the corresponding key, but I don't have the actual algorithm to decode the data. So this will come later on. So what do we plan to do next? Well, find what's missing. So essentially find the cipher. It's in the phone somewhere. Find the speech algorithm. Same thing. It's in the phone somewhere. Implement the upper layers. Try to, instead of manually coding all the message type, try to create code generators that can actually parse the specification and automatically generate marshalling and demarshalling methods. The transmit side, hopefully one day. If you want to implement something, feel free to do so. I'd like to take a moment to thank the people who contributed to this project. Most notably, Dimitri for doing all the groundwork in the early capture and writing the actual capture tool that is so easy to use. Harald for starting the project and getting us interested in GMR in the first place, and Steve for all the research he did into finding good way to capture the signal easily with readily available hardware. You can read the specification. As I said, you will need both the GMR spec and the GSM spec because there's a lot of reference. And you can visit the wiki. There is a lot of information as well as getting started and how to get things running. And that's it. Thank you for your attention. So do you have any question?
Any question? It was heavy, I know.
Okay.
Yeah, well, there's one question.
So what's your plan for getting the Cypher out of the phone? I mean, with the codec, it's probably a program on the DSP. I get that, but I would guess the Cypher is actual hardware.
Actually, it's not. Because we found someone who published, some Korean firm who developed the phone, published a paper about the architecture of the phone, and you can clearly see the Cypher unit being in the OMAP DSP processor. At first we thought it was in the because there is an ASIC in it, and we thought it's going to be in the ASIC. And then we found this paper which actually described the architecture of this ASIC, and you can see that it's not. The ASIC is purely software-defined radio stuff.
Do you have a dump of that firmware already, or is it off the phone, or do you need to get it out?
I'm sorry?
Do you have a dump of that firmware already, or do you need to get it out of the phone?
We have the firmware update. The firmware update files are available on the internet freely, and they load very nicely in ADA. So we actually have it. What we're looking for, though, is broken phones. So if you have some.
So presumably you, where, Sylvain?
Yeah, I'm sorry. Where are you?
There.
Oh, okay. Hi.
Hi. So presumably you will be able to use one of these broken phones to use it as a black box for the codec and the encryption.
Yeah, for the encryption, we're hoping to actually extract it, because encryption tends to be relatively easy to spot and extract. Usually, they're quite small. On the other hand, the speech codec is probably quite large, and so in the first time, maybe we'll just find how to feed the data to the phone, have it decompress, and get the data, or maybe just run the DSP image in a DSP emulator. I mean.
Yeah, here is a question from the net.
Yeah.
Can you sniff ARFCH channel data with standard hardware like Osmocom-BB?
No, you cannot use the Osmocom-BB phone hardware to sniff GMR channels, because the symbol rate is different, the frequency band is different, and well, that's quite enough actually. It just won't work.
I have a question. Are all the spots active all the time, or is it just when there's a phone you need to have a phone to activate some spots?
No,
or something?
the spot beams are all active at the same time. At least as far as we can see, as far as the spec is concerned. There are some provision to, I mean, they can reconfigure the spot if they want to, like, allocate more spot for an area because they have more subscribers or stuff like that. But spot beams are not activated on demand because the phones need the spot beam to synchronize. However, when a spot beam, as you saw on the capture, most of the time it's actually not transmitting anything. So, yeah, if there is nothing to say.
Are you aware of any currently available phones that you can use as a GMR modem, such as the analogous to GSM modem with 80 commands?
Yes, this one has 80 commands, and they also have dedicated modem. So there is no phone; it's just a data modem for data connection. Yeah.
Do you have any plans on emulating or studying the space section?
Yes. Actually, that's probably one of the first things we're going to try on the TIC side of things, because generating a static carrier beam should actually be fairly easy. We did it for GSM pretty quickly, just to make it appear in the network list. So I suspect that for GMR, it shouldn't be too hard to replicate that and have it running, yes.